There is a world at the edge of our solar system, where the sky is filled with a blue haze made of organic poison, where the ground is covered in nitrogen, ice cold enough to freeze the air itself out of existence, and where the feeble light of a sun 40 times farther away than ours barely reaches the surface. For decades, we treated this world like a harmless cartoon character, a tiny frozen underdog stripped of its planetary status. Then the James Webb Space Telescope turned its infrared eyes toward Pluto for the first time and revealed something that shattered the cute image forever. What Webb found is not a single terrifying secret. It is worse. Pluto is alive in ways that make the outer solar system feel darker, colder, and far more hostile than anyone imagined. If you enjoy journeys that change how you see reality, I would really appreciate it if you hit that like button and subscribe. It helps more than you know and keeps these deep dives coming. Also, we're now live on Spotify. The link's in the description if you'd like to listen wherever you are. Now, get yourself comfortable. Let's begin. Everyone loves Pluto. That is the problem. For nearly a century, human beings have treated this tiny frozen world at the edge of the solar system as a kind of cosmic pet, a lovable underdog. A sentimental favourite that got bullied by astronomers when they stripped away its planetary status and sent it to the back of the textbook. People wore t-shirts and put bumper stickers on their cars defending its planetary status. When NASA released the first close-up photographs in 2015, millions fell in love with a heart-shaped feature made of nitrogen ice and decided Pluto was adorable. And that is the image most people still carry in their minds. A small, pale, harmless snowball drifting quietly through the dark. Cute, quaint, a little sad maybe, the way a forgotten toy at the bottom of a box is sad. The ninth planet that was not a planet anymore. The misfit that got kicked out of the club. People feel protective of Pluto. They feel nostalgic about it. They project human emotions onto a lump of ice and rock that sits so far from the sun that noon on its surface looks dimmer than a cloudy twilight on Earth. This sentimental attachment is not harmless. It has built a mental image of Pluto that is almost entirely wrong. Not wrong in the sense that people get specific facts incorrect, although they often do. Wrong in the sense that the entire emotional framework is a fantasy. The real Pluto is not cute. It is not quaint. It is not a harmless little outcast drifting peacefully through the void. The real Pluto is one of the strangest, coldest, most chemically hostile worlds in our solar system. A place where the atmosphere itself may be in the process of freezing and collapsing onto the ground, where organic poisons rain from a blue haze that stretches hundreds of kilometers into a nearly black sky, and where the feeble glow of a distant sun provides so little warmth that the difference between day and night is measured in degrees that most humans have never experienced in any context. But you would never know any of this from the popular image. The popular image was built from decades of distance, sentimentality, and a handful of stunning but limited photographs. And it has taken the most powerful space telescope ever constructed to finally tear that image apart. When we say the James Webb Space Telescope scanned Pluto for the first time, we need to be precise about what that means. This is not the first time humans have seen Pluto. Pluto was discovered in 1930 by a young astronomer named Clyde Tombaugh working at Lowell Observatory in Arizona. Tombaugh spent months comparing photographic plates of the night sky, looking for a tiny point of light that moved against the background stars. When he found it, the discovery made international news. The world had a new planet, or so everyone believed for the next 76 years. For decades after its discovery, Pluto remained a mystery. It was so far away and so small that even the best telescopes on Earth could resolve it only as a faint dot. Scientists knew almost nothing about its surface, its composition, or its atmosphere. They could measure its orbit, a wildly eccentric path that takes 248 Earth years to complete, and they could estimate its size, which turned out to be shockingly small. Pluto is smaller than Earth's moon. Its diameter is roughly 2,380 kilometers, about two-thirds the width of the moon. If you place Pluto on top of the United States, it would barely stretch from New York to Dallas. This tininess fed the sentimental image, a world that small could not possibly be threatening or important. It was just a frozen pebble, a leftover from the formation of the solar system, a cosmic afterthought that happened to wander into the gravitational neighborhood of the giant planets. Then, in 1978, astronomers discovered that Pluto had a companion, a large moon, roughly half Pluto's own diameter, orbiting so close that the two bodies are effectively a double system. The moon was named Charon after the ferryman of the dead in Greek mythology, and its discovery immediately complicated the simple picture of Pluto as a lonesome drifter. This was not just a rock with a rock orbiting it. This was a gravitationally locked pair, tidally bound so that the same faces always point toward each other, spinning together through the darkness like two dancers frozen in position. In the decades that followed, astronomers discovered 4 more tiny moons, detected hints of an atmosphere through stellar occultation measurements, and began to suspect that the surface contained exotic ices frozen solid at temperatures that defy human experience. But all of this remained vague, seen through the equivalent of a frosted window from billions of kilometers away. The Hubble Space Telescope helped, but only slightly. Hubble could resolve Pluto as a small disk with blotchy light and dark regions. It was enough to confirm that Pluto's surface was varied, not a uniform ball of ice, but nowhere near enough to understand what was actually happening on the ground. Pluto remained a puzzle wrapped in distance and darkness. Then came New Horizons. On July 14, 2015, after a journey of 9.5 years and nearly 5 billion kilometers, NASA's New Horizons spacecraft screamed past Pluto at nearly 50,000 kilometers per hour. The flyby lasted only a few hours, but the data it returned transformed everything. The photographs were astonishing. Pluto's surface was not the featureless frozen wasteland that many scientists had expected. It was a world of staggering geological diversity. The western half of its face was dominated by a vast heart-shaped plain of nitrogen ice that the team informally named Tombor Regio after Pluto's discoverer. Within that heart sat Sputnik Planitia, an enormous basin roughly 1,000 kilometers across, filled with nitrogen ice so fresh and geologically active that it showed almost no impact craters. The ice was organized into polygonal convection cells, each one tens of kilometers wide, where warmer nitrogen rises from below, spreads across the surface, cools, and sinks again in a slow churning cycle that refreshes the landscape over timescales of roughly 500,000 years. Surrounding this icy plain rose mountains of water ice, some reaching 3.5 kilometers high. Water ice on Pluto behaves like bedrock. At temperatures of minus 230 degrees Celsius, water ice becomes structural bedrock. It does not flow. It does not sublimate. It simply sits there, forming the rigid crust upon which the softer, more volatile ices migrate and transform. The mountains had names that evoked the extremity of the landscape. Norgay Montes, Hillary Montes, named after earthly mountaineers who conquered Everest, as though Pluto's frozen peaks deserved the same reverence. On the opposite side of the heart, the terrain shifted dramatically. Dark equatorial regions coated in reddish-brown organic material stretched across the surface. Cthulhu Macula, a Darnark band named after a fictional cosmic horror, was covered in tholins, reddish-brown organic compounds produced by photochemistry high in the atmosphere, a slow rain of complex molecules that darken and discolor everything they touch. And above all of this hung the haze. New Horizons captured a breathtaking backlit image of Pluto as the spacecraft looked back after its closest approach, and the photograph revealed something nobody had fully anticipated. Pluto's thin atmosphere was filled with layer upon layer of blue haze, extending that currently towers high into Pluto's near-vacuum sky begins to thin. The haze was not a cloud, in any conventional sense. It was a suspended curtain of organic particles, tiny grains of complex hydrocarbons and nitriles created by photochemistry in the upper atmosphere. It scattered sunlight in the blue wavelengths, giving Pluto an ethereal blue glow that stood in eerie contrast to the frozen desolation below. The images were spectacular, they were beautiful, and they fed the sentimental narrative perfectly. Look at the heart, look at the blue sky. Pluto is gorgeous. Pluto is special. Pluto deserves to be a planet again. But here is what most people never understood about the New Horizons flyby. It was a snapshot, a single pass at enormous speed through a system that changes over decades and centuries. New Horizons carried visible light cameras and some infrared and ultraviolet instruments, but its observations were confined to a narrow window of time and a limited range of wavelengths. It could photograph the surface in stunning detail. It could measure the composition of the atmosphere at one moment in Pluto's 248-year orbit. It could detect the haze and measure its vertical structure. What it could not do is watch Pluto change. It could not measure the thermal glow of the surface and atmosphere in the mid-infrared wavelengths, where heat radiation reveals temperature variations across the globe. It could not separate Pluto's faint thermal signal from Charon's at those wavelengths because the two bodies are so close together and so far from Earth that their infrared emissions blend into a single unresolved source for any instrument operating from near-Earth space. It could not observe the haze over time to determine whether those organic particles were actively heating and cooling the atmosphere or merely floating passively in the sky. These were not minor gaps. They were fundamental limitations that left the deepest questions about Pluto's climate and atmospheric behavior completely unanswered. New Horizons told us what Pluto looked like at one instant. It could not tell us how Pluto works. That distinction matters enormously. A photograph of a landscape tells you what the terrain looks like today. But if you want to understand the weather, the seasons, the long-term forces shaping that landscape, you need sustained observation across time and across wavelengths that reveal processes invisible to the eye. You need to see heat. You need to measure chemistry. You need to watch the system breathe. This is exactly what the James Webb Space Telescope was built to do. Not specifically for Pluto, Webb was designed to study the earliest galaxies, distant exoplanet atmospheres, and star-forming regions across the universe. But its capabilities make it the most powerful instrument ever pointed at the outer solar system. Webb's primary mirror, 6.5 meters across, collects vastly more light than any previous space telescope. Its instruments operate in the infrared, from near-infrared wavelengths just beyond what human eyes can see all the way into the mid-infrared, where objects at Pluto's frigid temperatures emit their peak thermal radiation. The key instrument for Pluto is MIRI, the mid-infrared instrument. MIRI operates in wavelengths from roughly 5 to 28 micrometers. This is the spectral range where cold objects glow. Everything in the universe with a temperature above absolute zero emits thermal radiation, and for objects as cold as Pluto, that radiation peaks in the mid-infrared. MIRI can detect this faint glow, measure its intensity at different wavelengths, and extract information about surface temperature, composition, and atmospheric properties that no visible light camera can access. But MIRI had a specific challenge with Pluto that no previous instrument had been able to overcome. Pluto and Charon orbit each other at a separation of only about 19,600 kilometers. From Earth's perspective, nearly 5 billion kilometers away. That angular separation is tiny. Previous mid-infrared instruments lack the spatial resolution to distinguish between the two bodies. Their thermal signals merged into a single blurred point, making it impossible to know which features belong to Pluto and which belong to Charon. Webb changed that. Its combination of large mirror size and precise infrared optics gave MIRI just enough spatial resolution to separate the two worlds for the first time in mid-infrared wavelengths. This was not a dramatic visual separation like seeing two distinct disks. It was a careful photometric extraction, teasing apart the overlapping signals using the known orbital geometry of the system, and the telescope's ability to detect slight shifts in the combined brightness as Pluto and Charon moved relative to each other. The observations happened in two phases. In 2022, Webb's MIRI instrument measured the thermal emission from the Pluto-Charon system at 18, 21, and 25 micrometers. These measurements captured variations in heat output as both bodies rotated, revealing differences in surface temperature across their globes. Then, in 2023, MIRI obtained a full mid-infrared spectrum of Pluto from approximately 4.9 to 27 micrometers. This was the first time anyone had ever measured Pluto's thermal emission across this entire spectral range. Previous instruments simply could not detect such a faint signal from such a distant, cold object. The data arrived in fragments, as space telescope observations always do, transmitted across billions of kilometers, and then painstakingly processed by teams of researchers in France, the United States, and elsewhere. The analysis took months. The results were published in a series of papers in 2025 in the journals Astronomy and Astrophysics and Nature Astronomy. And what those results revealed was not comforting. To understand why, you need to appreciate what mid-infrared observations actually tell scientists that visible light photographs cannot. When you look at a photograph of Pluto taken by New Horizons, you are seeing reflected sunlight. The image shows you what the surface looks like in the same wavelengths your eyes would detect if you were floating above the landscape. Bright regions reflect more sunlight. Dark regions absorb more. The colors tell you something about surface composition, but they tell you almost nothing about temperature, atmospheric energy balance, or the physical processes driving Pluto's climate. Mid-infrared observations are fundamentally different. In the mid-infrared, you are not seeing reflected light. You are seeing emitted heat. Every surface on Pluto radiates thermal energy based on its temperature, and that radiation carries a spectral fingerprint that reveals not just how warm or cold the surface is, but what materials are present and how they interact with incoming solar energy. The atmosphere contributes its own infrared signature, and critically, so does the haze. If organic haze particles absorb sunlight and re-radiate it as infrared energy, that process shows up directly in the mid-infrared spectrum. It is invisible in photographs but unmistakable in thermal data. This is why Webb's scan of Pluto matters so much, and why calling it the first time is scientifically precise rather than sensational. Humanity had seen Pluto before. We had photographed it in extraordinary detail, but we had never measured its thermal behavior in the wavelengths where the most important climate processes reveal themselves. Webb did not give us a better picture of Pluto. It gave us a fundamentally different kind of information, the kind that transforms Pluto from a static portrait into a dynamic, evolving, physically active world. And the first thing that information revealed was something deeply strange about Pluto's atmosphere. Before Webb's observations, scientists already knew that Pluto's atmosphere was thin and exotic. New Horizons had confirmed that it consists almost entirely of nitrogen gas, with small amounts of methane and carbon monoxide. The surface pressure is roughly 1 pascal, about 100,000th of Earth's atmospheric pressure at sea level. Standing on Pluto, you would be in what any human would consider a hard vacuum, yet that wisp of gas is enough to create weather, drive ice migration across the surface, and support a towering column of photochemical haze that stretches hundreds of kilometers above the ground. In 2017, 2 years after the New Horizons flyby, a team led by planetary scientist Shi Jiang proposed a radical hypothesis. They suggested that Pluto's atmospheric haze was not merely a byproduct of photochemistry, but the primary driver of Pluto's climate. Their models showed that haze particles absorb ultraviolet sunlight during the day, warm up, and then radiate that energy away as infrared emission. This radiative cooling process, they argued, was far more efficient than cooling by atmospheric gases alone. If correct, it would explain a puzzling observation from New Horizons. Pluto's upper atmosphere was roughly 30 degrees Celsius, colder than models predicted based on gas-only cooling. The haze was acting like a vast radiative cooling system, absorbing solar energy and dumping it into space as infrared light, chilling the atmosphere well below what anyone expected. It was an elegant hypothesis. It was also untestable at the time. Confirming it required measuring Pluto's mid-infrared emission with enough precision to detect the thermal signature of the haze, and no instrument in existence could do that. The haze signal would be extraordinarily faint, buried within the combined thermal glow of Pluto and Charon, detectable only in wavelengths that ground-based telescopes struggle to observe due to Earth's own atmospheric absorption. The researchers made a prediction. They calculated exactly how bright Pluto should appear in specific mid-infrared wavelengths if the haze was actively radiating. They published those numbers and waited for a telescope powerful enough to check. Webb was that telescope. And when MIRI measured Pluto's mid-infrared emission for the first time, the numbers matched. The haze was glowing. Pluto's organic atmospheric particles were absorbing sunlight, heating up and radiating in the infrared, exactly as the 2017 model had predicted. The match between prediction and observation was remarkably close. close enough that the lead researcher on the original hypothesis called it rare in planetary science to have a theory confirmed so quickly. But confirmation of the haze cooling model was only the beginning of what Webb revealed. The thermal data showed something far more complex and far more unsettling than a simple cooling mechanism. Pluto's surface temperature varied dramatically as the dwarf planet rotated, with thermal emission shifting in patterns that traced the distribution of different ices across the globe. Nitrogen-rich regions radiated differently from methane-rich regions. Dark, tholin-coated terrain absorbed and re-emitted heat differently from the bright ice plains. The surface was not a uniform frozen shell. It was a patchwork of chemically distinct zones, each responding to the feeble sunlight in its own way, each participating in a volatile cycle that moves ices from one hemisphere to another over decades and centuries. And then there was Charon. Webb's ability to separate Charon's thermal signal from Pluto's revealed that Pluto's largest moon is a very different world. Charon showed no atmospheric signature. Its surface is dominated by water ice mixed with ammonia-bearing compounds, and it lacks the volatile ices that drive Pluto's climate. But Charon's polar regions told a different story. They were darker and redder than the rest of the moon, stained with organic material that had no local source. Webb detected carbon dioxide and hydrogen peroxide on Charon's surface, molecules that had never been confirmed there before. The implication was immediate and eerie. Methane molecules escaping from Pluto's atmosphere were drifting across the 19,600 kilometers of space between the two worlds, settling onto Charon's frigid polar regions and being transformed by ultraviolet radiation into reddish organic sludge. Pluto was not just losing its atmosphere into space. It was painting its own moon with chemical residue, an interaction that happens nowhere else in our solar system. This single detail should have been enough to destroy the cute image of Pluto forever. A world actively leaking molecules from its atmosphere onto a neighboring body where those molecules are chemically transformed into complex organic tar by radiation from a sun so distant it looks like a bright star. This is not the behavior of a harmless frozen snowball. This is the behavior of a chemically active, climatologically strange world operating under physical conditions that most people have never considered. But the Webb data contained far more than this. The mid-infrared spectrum of Pluto's atmosphere revealed the thermal fingerprint of a climate system that operates by rules found nowhere else in our solar system. Not on Earth, not on Mars, not on Venus or Titan or any of the giant planets. Pluto's haze does not merely cool the atmosphere from above. The particles themselves rise and fall within the atmosphere as they absorb and emit radiation, creating a dynamic cycle of heating and cooling that drives atmospheric behavior from the top down rather than from the surface up. On Earth, climate is driven primarily by surface heating. Sunlight warms the ground warms the air above it, and convection carries that heat upward. On Pluto, the surface is so cold and the atmosphere so thin that this mechanism barely operates. Instead, the haze particles suspended high in the atmosphere absorb what little ultraviolet energy the distant sun provides, warm slightly, radiate in the infrared, cool, and sink. New particles rise to take their place. The entire atmospheric energy balance is controlled not by the ground below, but by a suspended layer of organic particles above. One of the lead researchers described this as a new kind of climate, unique in the solar system, a world where the weather is made not of water or carbon dioxide or sulfuric acid, but of tiny grains of organic poison, drifting through a sky so thin it barely qualifies as an atmosphere at all. If you had told any planetary scientist 50 years ago that a dwarf planet at the edge of the solar system would turn out to possess a climate system unlike anything found on any other world, they would not have believed you. If you had told them that the key to understanding that climate would require a telescope that did not yet exist, measuring wavelengths that no previous instrument could detect from that distance, they would have considered it science fiction. But that is exactly what happened. The James Webb Space Telescope looked at Pluto in a way no one had ever looked before, and the first thing it confirmed is that Pluto's climate is driven by a mechanism that has no parallel anywhere else we have ever observed. The haze is real, the cooling is real, the atmospheric chemistry is real, and the implications extend far beyond Pluto itself. Because what Webb measured in Pluto's mid-infrared spectrum does not merely answer old questions, it opens new ones that are far more disturbing. If Pluto's haze controls its climate, what happens as Pluto moves farther from the Sun on its long elliptical orbit and the already feeble ultraviolet input drops even further? What happens to the atmosphere as temperatures continue to fall? What happens to the volatile ices that are even now migrating across the surface in response to shifting seasons that last longer than the entirety of recorded human civilization? The Webb data suggests that Pluto is not simply sitting in the cold. It is actively changing, decade by decade, in ways that make it more alien and more hostile the closer we look. And the next phase of that story, the physical reality of what those changes mean, is far worse than the sentimental image ever prepared anyone to hear. The data arrived as numbers, not photographs, not dramatic images, not the kind of visual spectacle that makes people share a picture and say, "Look at this." What the James Webb Space Telescope captured from Pluto was a series of measurements in mid-infrared wavelengths, flux values at specific points across the electromagnetic spectrum, thermal brightness readings taken as Pluto slowly rotated over hours of observation. To a non-scientist, the raw output looks like nothing more than a spreadsheet. Columns of figures, error bars, calibration corrections. But inside those numbers was a revelation that upended decades of assumptions about how a world at the edge of the solar system actually functions. The first and most important result was confirmation that Pluto's atmosphere operates like nothing else ever observed on any planet or moon. When researchers extracted the mid-infrared spectrum of Pluto across wavelengths from approximately 4.9 to 27 micrometers, they found a thermal signature that could not be explained by surface emission alone. Something in the atmosphere was radiating powerfully in the infrared. Something was converting absorbed solar energy into thermal radiation and broadcasting it outward into space with an efficiency that the thin atmospheric gases by themselves could never achieve. That something was the haze. To understand what makes this so extraordinary, consider how climates normally work in our solar system. On Earth, the sun warms the surface. The surface warms the lower atmosphere through direct contact and convection. Greenhouse gases trap some of that heat, raising the average temperature. The climate is driven from the bottom up. Surface heating is the engine. Atmospheric gases modulate how much heat escapes. This basic architecture, with local variations, applies to Venus, Mars, and even the giant planets in modified forms. Pluto breaks this architecture completely. On Pluto, the surface is so cold, hovering between roughly 40 and 60 Kelvin, that it radiates very little thermal energy. The atmosphere is so thin that it cannot trap meaningful amounts of heat through any greenhouse mechanism. There is no convective engine churning warm air upward from the ground. The entire atmospheric column contains so little gas that if you compressed Pluto's atmosphere to the surface pressure of Earth, it would form a layer thinner than a coat of paint. Pluto's surface pressure is comparable to the conditions found at roughly 80 kilometers above Earth's surface, an altitude where the atmosphere has thinned to almost nothing, well above where any aircraft can fly, at the threshold of what engineers define as outer space. By any terrestrial standard, Pluto has no atmosphere at all. It exists in what should be a state of pure radiative equilibrium, with the distant sun, a frozen surface absorbing tiny amounts of sunlight and re-emitting that energy into space with nothing in between to complicate the process. But something does complicate the process. High above the surface, stretching from roughly 10 kilometers altitude to more than 300 kilometers, a vast column of organic haze particles hangs in the near vacuum. These particles are not gas molecules. They are solid grains, tiny aggregates of complex hydrocarbons and nitrogen-bearing organic compounds, created when ultraviolet radiation from the sun breaks apart methane and nitrogen molecules in the upper atmosphere. The fragments recombine into increasingly complex chains and rings, forming molecules like acetylene, ethylene, hydrogen cyanide, and eventually larger polymeric structures that condense into tiny solid particles. These particles are incredibly small, measured in fractions of a micrometer, and they descend through the atmosphere with excruciating slowness, drifting downward over months and years before eventually reaching the surface and contributing to the dark reddish-brown coating of tholins that stains Pluto's equatorial regions. New Horizons photographed this haze in stunning backlit images. It appeared as concentric blue layers floating above the limb of the planet, luminous and delicate, giving Pluto the appearance of a world wrapped in ghostly silk. The images were beautiful. They were also deeply misleading about the haze's actual role in Pluto's environment. Because the haze is not decoration, it is the climate. What Webb's MIRI instrument measured for the first time is the thermal emission from these haze particles themselves. When ultraviolet photons from the sun strike the organic grains, the particles absorb that energy and warm up, not by much. These are not hot particles by any human standard, but they warm enough to radiate in the mid-infrared, emitting photons at wavelengths between roughly 15 and 25 micrometers. This emission carries energy away from the atmosphere and dumps it into space. The effect is a net cooling of the atmospheric column, driven not by gases but by suspended solid particles acting as radiative emitters. The scale of this cooling stunned researchers. Models had predicted that if the haze were radiatively active, it would cool Pluto's upper atmosphere by approximately 30 degrees Celsius, below what gas phase cooling alone could achieve. When New Horizons measured atmospheric temperatures during its flyby, it found that the upper atmosphere was indeed far colder than expected, roughly -203 degrees Celsius at altitudes, where models based on gas cooling predicted temperatures closer to -170 degrees Celsius. The discrepancy was enormous. Something was pulling heat out of the atmosphere far more efficiently than nitrogen and methane gas could manage. The 2017 hypothesis by Shi Jiang and colleagues proposed the haze as the answer. Webb confirmed it. The mid-infrared brightness of Pluto matched the predicted haze emission signature with remarkable precision. The haze particles were glowing in the infrared exactly as the models had calculated they would if they were the dominant cooling agents in the atmosphere. For the first time, scientists had direct observational evidence that a planetary climate was being controlled not by greenhouse gases, not by surface processes, not by atmospheric circulation, but by a suspended layer of organic particles that absorb sunlight and radiate heat into the void. Tanguy Bertrand, the astronomer at the Paris Observatory who led the analysis of the Webb data, described this as a new kind of climate, unique in the solar system. No other world operates this way. On Triton, Neptune's largest moon, a similar thin nitrogen atmosphere exists, but its haze is far less developed and its climate dynamics are different. On Titan, Saturn's largest moon, a thick haze of organic particles fills the atmosphere, but Titan's atmosphere is dense enough that gas phase processes dominate the energy balance. Pluto occupies a strange intermediate zone, where the atmosphere is too thin for gases to control the climate, but thick enough to support a haze column that does the job instead. It is a climate driven by a thermostat wired in reverse, one that cools the atmosphere from above rather than warming it from below. But the haze cooling discovery was not the only thing MIRI revealed. The thermal data contained a second layer of information that proved even more unsettling when scientists began to unpack its implications. As Pluto rotated during the hours of Webb observation, MIRI recorded how the thermal emission changed across different longitudes of the surface. These thermal light curves, measurements of brightness variation at 18, 21, and 25 micrometers, as the planet turned, revealed dramatic differences in surface temperature from one region to another. Bright nitrogen ice plains radiated differently from dark tholin-coated terrain. Methane-rich highlands produced a distinct thermal signature compared to the vast nitrogen glaciers of Sputnik Planitia. The mid-infrared data painted a temperature map of Pluto's surface that visible light cameras could never provide. What this map showed is that Pluto's surface is not a static frozen shell. It is a dynamic patchwork of volatile ices in constant slow migration, driven by the interplay between feeble solar heating, extreme axial tilt, and the wildly eccentric orbit that carries Pluto from roughly 30 astronomical units from the Sun at its closest approach to nearly 50 astronomical units at its farthest. 1 astronomical unit is the distance from Earth to the Sun, so Pluto's orbit takes it from 30 times that distance to nearly 50 times that distance over the course of 248 years. This enormous variation in solar distance means that the amount of energy reaching Pluto's surface changes dramatically over a single Plutonian year. At closest approach, which last occurred in 1989, Pluto receives nearly 3 times as much solar energy as it does at its farthest point. That difference is enough to drive a global volatile cycle unlike anything found on any other world. Here is how that cycle works, and why Webb's thermal measurements made it visible in a way that was never possible before. Nitrogen, the dominant surface and atmospheric constituent, exists as solid ice at Pluto's temperatures. When sunlight strikes nitrogen ice, even the dim sunlight reaching Pluto's distance, it provides just enough energy to sublimate the ice directly from solid to gas. The nitrogen vapor enters the atmosphere, contributing to the thin gaseous envelope. As Pluto's extreme axial tilt of approximately 120 degrees causes different regions to be illuminated or shadowed over the course of its orbit, nitrogen sublimates from sunlit areas and refreezes in colder, shadowed zones. The ice migrates, literally. Nitrogen leaves one hemisphere, travels through the atmosphere, and deposits itself on the other side of the planet. This volatile transport cycle operates on timescales of decades to centuries. Sputnik Planitia, the vast heart-shaped nitrogen ice basin, acts as a cold trap because it sits at a lower elevation where atmospheric pressure is slightly higher and nitrogen condensation occurs more readily. The basin accumulates nitrogen from other regions, maintaining its fresh, crater-free appearance. Meanwhile, other parts of the surface lose their nitrogen coating and are left exposed, bare water ice bedrock or tholin-stained terrain, baking under the faint ultraviolet glare. Webb's thermal measurements captured this volatile distribution in action. Regions rich in nitrogen ice showed different mid-infrared emission characteristics than regions where methane ice dominated the surface. Methane and nitrogen have different thermal properties, different emissivities, different responses to incoming solar radiation. By measuring how the thermal brightness changed with wavelength across the mid-infrared spectrum, scientists could determine not just where the ices were, but how they were interacting with the energy environment. The data revealed that the volatile cycle is not a simple back and forth between two hemispheres. It is a complex multi-species process involving nitrogen, methane, and carbon monoxide, each with different volatilities, different freezing points, and different spatial distributions across the surface. Methane, in particular, behaves strangely on Pluto. It is less volatile than nitrogen, meaning it sublimates at slightly higher temperatures and tends to accumulate in different locations. New Horizons had already shown that methane ice concentrates on Pluto's higher elevations, the mountain peaks and ridgelines, while nitrogen fills the valleys and basins. The explanation is altitude-dependent temperature variation combined with differences in sublimation pressure. But Webb's thermal data added a new dimension. The methane-rich regions showed thermal behavior, suggesting that methane ice on Pluto's surface is not uniform in texture or grain size. Some areas appeared to contain large crystals of methane ice with different thermal inertia than areas with fine-grained methane frost. This textural variation affects how quickly different regions heat up during the day and cool down at night, creating a surface thermal environment that is far more complex than a simple layer of frozen gas. The thermal light curves that MIRI recorded as Pluto rotated revealed something else that no previous observation had been able to capture. The contrast between Pluto's dayside and nightside thermal emission was measurable and significant, but it did not follow the simple pattern that scientists would expect from a uniform icy surface. On a world with no atmosphere and a single type of surface ice, the dayside would warm slightly under solar illumination, and the nightside would cool rapidly as it rotated into shadow. The thermal curve would be smooth, predictable, a gentle sine wave tracking the planet's rotation period. Pluto's thermal curve was not smooth. It was lumpy, irregular, marked by distinct peaks and troughs that corresponded to specific surface regions rotating in and out of the MIRI field of view. When the nitrogen ice plains of Sputnik Planitia faced the telescope, the thermal signature shifted in one direction. When the dark tholin-coated terrain of the equatorial regions rotated into view, the signature changed character. When methane-rich highland regions dominated the visible hemisphere, the curve shifted again. Each surface type responded to the meager solar input with a different thermal inertia, a different rate of warming during the day and cooling during the night, a different efficiency at absorbing and re-emitting infrared radiation. Thermal inertia is a measure of how quickly a surface responds to changes in heating. A surface with high thermal inertia warms slowly during the day and cools slowly at night, maintaining relatively stable temperatures. A surface with low thermal inertia heats up quickly and cools down quickly, swinging between extremes. On Earth, oceans have high thermal inertia and deserts have low thermal inertia, which is why coastal climates are milder than inland continental climates. On Pluto, the thermal inertia differences between nitrogen ice, methane ice, water ice bedrock, and tholin-coated terrain create a patchwork of thermal zones that respond to sunlight on completely different timescales. Webb's ability to detect these differences matters because it transforms Pluto from a single temperature world into a thermally complex landscape that can be monitored and mapped over time. New Horizons captured one flyby, one moment, one set of conditions. Webb can return to Pluto year after year, measuring how the thermal map changes as the planet recedes from the Sun, as volatile ices migrate, as the atmosphere thins, as the haze evolves. For the first time, scientists have an instrument capable of watching Pluto's climate change in something approaching real time, not geological time, not the deep time of orbital mechanics, but the timescale of years and decades during which measurable shifts in surface temperature and atmospheric structure are actively occurring. Each return visit will add another frame to a movie of planetary transformation that no previous generation of astronomers could have watched unfold. Carbon monoxide, the third major volatile species, added yet another layer of complexity. It is intermediate in volatility between nitrogen and methane, and it tends to be mixed with nitrogen ice in the large plains regions. Webb's spectral data was sensitive enough to detect the thermal contribution of carbon monoxide ice, showing that it participates in the same global transport cycle as nitrogen but with subtly different timing and distribution. The picture that emerged from the combined Webb data was of a world in constant slow chemical and physical transformation. Ices sublimate from one region, drift through the atmosphere as gas, refreeze in another location, are buried by new deposits, are exposed again by sublimation decades later. The surface Pluto presents to the universe at any given moment is a temporary configuration in a cycle that has been running for millions of years and will continue for millions more. The dwarf planet that most people imagine as a fixed frozen landscape is actually reshuffling its surface chemistry on timescales that, while long compared to human life, are geologically rapid. And then there is the transfer to Charon. This is perhaps the eeriest detail in the entire Webb dataset, and one that deserves careful explanation because it reveals a process that has no counterpart anywhere else in our solar system. Pluto's atmosphere, thin as it is, extends far above the surface. The exobase, the altitude above which atmospheric molecules are more likely to escape into space than collide with another molecule, sits roughly 1,700 kilometers above the ground. At and above this altitude, individual gas molecules that happen to be moving fast enough can escape Pluto's weak gravity entirely. Nitrogen molecules, being relatively heavy, mostly stay bound. But methane molecules, lighter and more energetic in the upper atmosphere, have a significant probability of escaping. When these methane molecules leave Pluto's gravitational influence, they do not simply vanish into interplanetary space. Some of them travel across the relatively short gap between Pluto and Charon and encounter the Moon's surface. Charon has no atmosphere of its own. It has no mechanism to stop or redirect incoming molecules. The methane simply arrives and sticks, freezing onto the frigid surface. But it does not remain as methane for long. Charon's polar regions spend decades in continuous darkness during the long Plutonian winter. Temperatures plunge to roughly minus 258 degrees Celsius, 15 Kelvin, cold enough to trap even nitrogen as a solid. During these long winters, methane molecules accumulate on the poles. When spring eventually returns and sunlight reaches the polar regions again, the temperature rises enough to sublimate the nitrogen and carbon monoxide back into vapor, which escapes Charon's weaker gravity. But the methane does not leave. It is less volatile than nitrogen and remains frozen while the lighter ices depart. Now exposed to ultraviolet sunlight without an atmospheric shield, the methane ice undergoes photolysis. Ultraviolet photons shatter the methane molecules, breaking carbon-hydrogen bonds and liberating fragments that recombine into heavier organic compounds. Ethane, acetylene, and progressively more complex hydrocarbons form on the surface, darkening it. Over thousands and millions of years, these compounds polymerize into tholins, the same class of reddish-brown organic sludge found on Pluto's equatorial regions. The result is the dark reddish polar caps that New Horizons photographed on Charon, features so prominent they were given a name from mythology. The northern cap was informally named after a dark fictional realm, a stain on an otherwise pale, icy world. Webb's near-infrared spectrograph, a separate instrument from MIRI, had already confirmed this process in earlier observations published in 2024. Those measurements detected carbon dioxide and hydrogen peroxide on Charon's surface for the first time, molecules that had never been identified there before. Carbon dioxide likely forms through radiation-driven chemistry involving carbon monoxide and water ice, while hydrogen peroxide arises from the radiolysis of water ice bombarded by solar ultraviolet and charged particles from the solar wind. The Webb data thus revealed a chemical system spanning two worlds. Pluto produces volatile gases through sublimation and photochemistry. Some of those gases escape the planet entirely and cross interplanetary space. They land on Charon, undergo further chemical transformation driven by ultraviolet radiation, and produce complex organic compounds that permanently alter the Moon's surface appearance. Pluto is slowly, continuously contaminating its own satellite with processed atmospheric waste. It is a one-directional chemical conveyor belt operating across nearly 20,000 kilometers of vacuum. No other planet-moon system in the solar system does this. Mars does not deposit atmospheric material on Phobos. Jupiter does not stain Io's surface with molecules from its own magnetosphere in this manner. The Pluto-Charon interaction is unique, a consequence of the system's specific combination of thin escaping atmosphere, close orbital proximity, weak gravity, extreme cold, and centuries-long seasonal cycles. It is the kind of process that nobody would have predicted from first principles, and that required both New Horizons and Webb to fully characterize. But even beyond the Charon transfer, the Webb data revealed something about Pluto's haze that makes the dwarf planet's atmosphere genuinely unlike any other known atmosphere. The haze particles do not simply float at a fixed altitude and radiate passively. The thermal data suggests they participate in a dynamic cycle of vertical motion tied directly to their radiative behavior. During the Plutonian day, such as it is with the Sun appearing as a distant bright point rather than a warming disk, ultraviolet photons strike the haze particles high in the atmosphere. The particles absorb this energy and warm up slightly. As they warm, they radiate more efficiently in the infrared, emitting heat into space. This emission cools them back down. But the warming and cooling are not instantaneous. There is a thermal lag, a period during which the particle's temperature is slightly elevated. During this period, the particle is slightly more buoyant in the surrounding atmospheric gas. As it cools and its thermal emission peaks, it becomes denser and begins to sink. Meanwhile, new particles forming at higher altitudes through ongoing photochemistry begin their own cycle of absorption, warming, emission, and descent. The result is a continuous, slow vertical circulation of haze particles, not driven by convection in the traditional sense, but by the interplay between radiative heating and gravitational settling. The haze column breathes. Particles rise and fall as they absorb and release energy. The atmosphere's thermal structure is shaped not by wind patterns or pressure gradients, but by the radiative behavior of trillions of individual organic grains, responding to the meager pulse of a sun so distant that its warmth is virtually undetectable on the surface. Bertrand and his team emphasized that this mechanism has never been observed on any other world. On Earth, aerosol particles influence climate through scattering and absorption, but they are minor players compared to greenhouse gases and ocean circulation. On Titan, organic hazes are thick and opaque, forming a smog layer that shapes surface temperatures, but Titan's dense atmosphere supports gas phase dynamics that dominate the climate. On Pluto, the haze is the climate. Remove it, and the atmospheric temperature profile would look completely different. The energy balance would shift, the volatile cycle would change, the entire character of the world would be altered. This realization landed with significant force in the planetary science community when the results were published. Researchers who study exoplanet atmospheres took immediate notice. because haze-driven climate processes have been proposed as possible explanations for puzzling observations of small, cold worlds orbiting distant stars. If Pluto demonstrates that organic haze can dominate a planetary energy balance under the right conditions, then similar processes might operate on sub-Neptune exoplanets, super-Earths with thin atmospheres, or tidally locked worlds receiving minimal stellar radiation. Pluto, the solar system's most famous former planet, suddenly became a laboratory for understanding atmospheric physics on worlds we may never visit. But the implications extend even closer to home. The same team that confirmed the haze cooling hypothesis pointed out a provocative parallel with early Earth. Before the rise of oxygen roughly 2.5 billion years ago, Earth's atmosphere was rich in methane and nitrogen but contained no free oxygen. Under those conditions, photochemistry would have produced organic haze particles similar in composition to those found on Pluto and Titan. Some researchers have proposed that early Earth was periodically shrouded in an organic haze that influenced surface temperatures, shielded the surface from ultraviolet radiation, and may have played a role in the chemical conditions that led to the origin of life. If Pluto's haze-driven climate provides a working example of how organic particles can dominate a planetary energy balance, it offers a natural laboratory for testing hypotheses about conditions that may have existed on Earth billions of years ago. The dwarf planet at the edge of the solar system may hold clues to how our own world became habitable. The irony is sharp. Pluto, the world most people think of as dead and irrelevant, might teach us something fundamental about the living world we call home, but none of this should be confused with comfort. The Webb data does not make Pluto more familiar. It makes Pluto more alien. Every layer of detail that the mid-infrared observations add to the picture pushes the dwarf planet further from the cozy image that people carry in their minds. The haze is not a beautiful blue veil. It is a radiative cooling system made of organic poison that chills the atmosphere to temperatures where even nitrogen freezes. The volatile cycle is not a gentle seasonal rhythm. It is a planetary-scale redistribution of surface material driven by a sun so far away that it appears as a cold, bright star in a nearly black sky. The transfer to Charon is not a charming quirk of a double-world system. It is a one-way chemical contamination process that permanently alters the receiving body. And all of this raises a question that Webb's data frames but does not fully answer. A question that becomes more urgent the more carefully scientists examine what the telescope measured. If Pluto's climate is driven by haze, and the haze is driven by ultraviolet sunlight, and Pluto is currently moving farther from the Sun on its long eccentric orbit, receiving less energy with each passing decade, what happens next? What happens to the haze when the ultraviolet input drops below the threshold needed to sustain its production? What happens to the atmosphere when the volatile cycle slows, when nitrogen stops sublimating, when the thin gaseous envelope that supports the haze begins to collapse? The Webb data does not show a world in equilibrium. It shows a world in transition. Pluto's atmosphere reached its maximum extent sometime around the late 20th century, driven by thermal lag from the 1989 closest approach to the Sun. Now, as the dwarf planet recedes, that maximum is past. The atmosphere has begun to change. Ground-based measurements already suggest that Pluto's atmospheric pressure is declining, slowly, almost imperceptibly, but measurably. The process that drives Pluto's strange climate may also be the process that eventually destroys it. What lies ahead for Pluto is not simply a colder winter. It is something far stranger and far more extreme than any seasonal change on any world closer to the Sun. And understanding what that change means requires confronting the physical reality of Pluto's environment in terms that the sentimental image never prepared anyone to consider. The numbers in Webb's data are not just measurements, they are warnings. They describe a world balanced on a knife edge between having an atmosphere and not having one, between chemical activity and frozen silence, between a dynamic volatile cycle and a surface locked in ice so cold that nothing moves, nothing sublimates, nothing changes for decades at a time. Pluto's climate is not merely unusual, it is precarious. And the telescope that finally revealed how it works also revealed just how close that climate may be to shutting down entirely. Stand on the surface of Pluto at local noon. Look up. Find the Sun. It is there, but it does not look like the Sun you know. It does not fill the sky with warmth and blinding light. It does not cast sharp shadows or heat your face. From Pluto's average distance of roughly 39 astronomical units, the Sun appears as a single brilliant point of light in a sky that remains functionally black even at midday. It is bright enough to read by, about 250 to 300 times brighter than a full moon seen from Earth, but it delivers almost no warmth. The total solar energy arriving at Pluto's surface is approximately 1/1500th of what reaches Earth. Imagine standing in a vast cathedral, completely dark except for a single candle burning at the far end of the nave. You can see the flame, you can tell it exists, but it does not warm the stone beneath your feet. That is the Sun from Pluto. This is the first physical fact that the sentimental image of Pluto quietly hides. When people look at photographs of Pluto's surface taken by New Horizons, they see a world lit clearly enough to reveal mountains, plains, and geological features in vivid detail. The photographs look bright. They look almost inviting, in a frozen, alien sort of way. But those photographs were taken by a spacecraft flying past the planet at close range, using cameras designed to collect every available photon and produce images with adjusted exposure and contrast. The human experience of standing on that surface would be radically different from what the photographs suggest. At local noon on Pluto, the landscape would appear bathed in a dim, bluish twilight. Colours would be muted. The horizon would fade into darkness within a few kilometres. The sky above would be black, except for the point of the Sun and a scattering of visible stars that would remain present even during the day because Pluto's atmosphere is far too thin to produce the bright blue scattering that hides stars in Earth's daytime sky. The haze layers above would be invisible to the naked eye at most altitudes, too sparse and too finely distributed to see without backlit illumination. You would stand in a landscape that is simultaneously sunlit and dark, a paradox created by the immense distance between this world and the source of all warmth in the solar system. Now consider what that feeble sunlight means for temperature. Pluto's surface temperature hovers between approximately 40 and 60 Kelvin. In more familiar terms, that is between roughly -233 and -213 degrees Celsius, or roughly -387 to -352 degrees Fahrenheit. These numbers are so far below any temperature humans normally encounter that they lose all intuitive meaning. Nothing in ordinary experience prepares you for what 40 Kelvin actually feels like, because nothing in ordinary experience comes remotely close. At these temperatures, the familiar categories of solid, liquid, and gas rearrange themselves in ways that defy everyday intuition. Nitrogen, the gas that makes up 78% of every breath you take on Earth, exists as a solid crystal on Pluto's surface. It forms vast ice plains that behave like glaciers, flowing slowly under their own weight. Water, the substance most people associate with ice and cold, is frozen so thoroughly at Pluto's temperatures that it becomes as rigid and immovable as granite. Water, ice on Pluto, does not flow. It does not crack under normal geological stresses. It forms the permanent bedrock of the crust, the structural foundation upon which the softer, volatile ices migrate and transform. Methane, the gas that burns in your kitchen stove, freezes into solid ice crystals on Pluto's highland ridges and peaks. Carbon monoxide, a colourless poison gas on Earth, solidifies and mixes with the nitrogen ice in the basin floors. Every substance that exists as a harmless or familiar gas in Earth's environment becomes a frozen mineral on Pluto. The entire surface is made of materials that on Earth would be invisible atmospheric gases. Pluto's landscape is constructed from its own frozen sky. This fact alone should unsettle anyone who thinks carefully about it. We are accustomed to worlds with surfaces made of rock, soil, metal, perhaps water ice in polar regions. Pluto's surface is made of frozen gases. The ground beneath your feet would be solid nitrogen. The mountains on the horizon would be water ice as hard as stone. The frost patterns on the plains would be methane and carbon monoxide crystals condensed from an atmosphere so thin it barely exists. You would be walking on a landscape made entirely of substances that, at any temperature comfortable for human life, would vanish into invisible vapor. The ground itself would evaporate if you could somehow warm it. And the ground does evaporate. That is the volatile cycle that Webb's thermal measurements revealed in action. When sunlight reaches the nitrogen ice plains, even the pitiful trickle of energy arriving from 1/1500th of Earth's solar input, it provides just enough thermal energy to sublimate the nitrogen directly from solid to gas. Individual molecules break free of the crystal lattice, drift upward into the thin atmosphere, and travel across the planet before refreezing in colder, shadowed regions. This is not a metaphor. The ground on Pluto literally evaporates and reforms somewhere else. The surface is transient, a temporary configuration of frozen volatiles that rearranges itself over decades and centuries in response to the shifting geometry of sunlight. Webb's infrared data showed this process through the thermal signatures of different ice species distributed unevenly across Pluto's surface. But the data also pointed towards something more ominous, something that connects Pluto's feeble sunlight to the potential fate of its atmosphere. Pluto reached its closest approach to the Sun, its perihelion, in 1989 at a distance of approximately 29.7 astronomical units. This was the warmest Pluto had been in 248 years, and the warmest it would be for another 248 years. At perihelion, the increased solar energy drove greater sublimation of surface ices, inflating the atmosphere to its maximum extent. Atmospheric pressure rose, the haze thickened, the volatile cycle accelerated. But Pluto has long since passed that peak. It is now receding from the Sun on the outbound leg of its enormous elliptical orbit, and it will continue receding for over a century. As the distance grows, the solar energy reaching the surface drops. Less energy means less sublimation. Less sublimation means less atmospheric gas. And less atmospheric gas means declining surface pressure. This decline has already been measured. Ground-based astronomers monitoring Pluto through stellar occultations, events where Pluto passes in front of a background star and its atmosphere refracts the starlight in detectable ways, recorded that Pluto's surface pressure decreased from approximately 1 pascal in 2015 to roughly 0.91 pascals by 2020, a drop of about 9% in 5 years. That number might sound trivial. 9% of an already minuscule pressure seems like nothing worth worrying about. But on a world where the atmosphere exists only because surface ices are warm enough to sublimate, any pressure decline is a signal that the balance is tipping. The atmosphere is not a permanent feature of Pluto. It is a temporary phenomenon, sustained only during the relatively brief portion of Pluto's orbit when it is close enough to the Sun for volatile ices to maintain their gaseous state against the background of cosmic cold. What happens as Pluto continues to recede is a question that planetary scientists have debated for decades, and it remains one of the most fascinating unresolved problems in outer solar system science. The leading models predict that as solar energy continues to drop, nitrogen sublimation will slow, atmospheric pressure will decline further, and at some point over the coming decades to centuries, a critical threshold will be crossed. The atmosphere will begin to collapse. Atmospheric collapse on Pluto does not mean a sudden catastrophic event. It is not an explosion or a rupture. It is more like a lake slowly draining through a crack in its own floor. As temperatures fall, the sublimation rate drops below the condensation rate. More nitrogen freezes onto the surface than sublimates off it. The atmosphere gradually deflates. Pressure drops. The haze thins because there is less methane in the upper atmosphere to feed photochemical production. The volatile cycle weakens. Eventually, the atmosphere becomes so thin that it ceases to function as a meaningful gaseous envelope. What remains is a surface-bound frost layer and a near-perfect vacuum above. The timeline for this process is uncertain. Some models predict the atmosphere will be largely collapsed within a few decades. Others suggest thermal inertia. In the nitrogen ice reservoirs of Sputnik, Planeti R, will sustain sublimation for much longer, potentially maintaining a detectable atmosphere for over a century even as Pluto recedes. The answer depends on parameters that are still poorly constrained: the total volume of nitrogen ice available for sublimation, the thermal conductivity of the surface layers, the albedo of different ice deposits, and the feedback effects of the haze itself. If the haze contributes to atmospheric cooling, as Webb has now confirmed, then it accelerates the collapse. A colder atmosphere means faster condensation, which means faster pressure decline, which means less haze production, which means less cooling, but also less ultraviolet absorption. The feedback loops are tangled and not yet fully understood. But even before the atmosphere reaches full collapse, the intermediate stages would transform Pluto's surface in ways that are difficult to visualize without confronting the physical details directly. As atmospheric pressure declines, the first change occurs in the haze column. Haze production depends on ultraviolet photolysis of methane in the upper atmosphere. As Pluto recedes from the Sun and ultraviolet flux drops, less methane is broken apart, fewer organic fragments are produced, and the rate of haze particle formation slows. The towering column of organic grains that currently extends more than 300 kilometers above the surface begins to thin. Not suddenly, not visibly from one year to the next, but steadily, over decades, the haze becomes sparser. Fewer particles means less radiative cooling, which might seem like it would warm the atmosphere, but it also means less ultraviolet absorption, which reduces the energy input to the haze layer. The two effects partially cancel, but the net result is an atmosphere that is both thinner and less thermally active. The climate engine does not merely slow down, it loses components. The mechanism that made Pluto's atmosphere unique begins to dismantle itself. On the surface, the consequences of declining pressure would manifest as a gradual shift in the geography of ice. Nitrogen sublimation slows as temperatures drop and pressure declines. The volatile transport cycle that currently moves nitrogen from sunlit regions to shadowed basins weakens. Sputnik Planitia, the great nitrogen ice reservoir, continues to accumulate material, but at a diminishing rate. Other regions that once lost nitrogen to sublimation begin to retain their ice coatings for longer periods. The surface becomes more uniformly frosted as the selective evaporation that created Pluto's distinctive patchwork of bright and dark terrain slows toward equilibrium. Methane, being less volatile than nitrogen, persists longer on the surface even as nitrogen activity declines. This creates a transitional period where Pluto's surface chemistry shifts. Regions that were previously dominated by nitrogen ice become methane-rich as the nitrogen sublimates away and is not replenished at the same rate. The spectral character of the surface changes. Albedo patterns shift. The familiar geography recorded by New Horizons gradually becomes unrecognizable, not through any dramatic event, but through the slow redistribution of surface materials responding to changing thermal and pressure conditions. Meanwhile, the organic material that was previously falling from the haze as a slow rain of tholin particles begins to accumulate differently. With less haze production, less tholin material reaches the surface per year, but the existing deposits remain. The dark equatorial bands do not brighten, they simply stop darkening at the rate they once did. Over centuries, the tholin layer becomes a fossil record of a more active atmospheric era, a stain left behind by a climate system that has largely shut down. The most haunting aspect of this transition is its silence. There is no dramatic moment, no catastrophic freeze, no visible event mark the change from a world with an atmosphere to a world without one. The transition occurs in increments too small for any single observation to capture. A fraction of a pascal of pressure lost per decade, a slight thinning of the haze column, a gradual slowing of the volatile cycle. An astronomer observing Pluto in 2050 would see a world that looks almost identical to the one Webb observed in 2022. An astronomer in 2100 might notice measurable differences. An astronomer in 2200 might struggle to detect an atmosphere at all. The change is real, physical, and relentless, but it unfolds on a timescale calibrated to Pluto's own unhurried rhythm, rather than to any human sense of urgency. The surface during the late stages of atmospheric collapse would be a landscape of extraordinary stillness. No sublimation plumes, no volatile transport, no haze particles drifting downward through a thin sky. Just ice, cold beyond comprehension, sealed under a vacuum so complete that individual molecules on the surface have essentially no chance of encountering another gas phase molecule above them. The nitrogen ice that once participated in a global cycle of evaporation and redeposition would sit motionless, locked in place by temperatures so low that the thermal energy available to any individual molecule falls far below the threshold needed to break free of the crystal lattice. The surface would not be dead in the biological sense, because it was never alive, but it would be dead in the thermodynamic sense, a system in which nothing moves, nothing changes, nothing transforms, until the long orbit carries Pluto back toward the Sun and the entire cycle begins again. What is clear is that Pluto's atmosphere is not a permanent feature. It is a seasonal phenomenon on a world where a single season lasts longer than the entirety of Western civilization. The atmosphere inflates near perihelion and deflates near aphelion. We happen to discover Pluto and study it during the period when its atmosphere was near its maximum extent. Future generations of astronomers may point their telescopes at Pluto and find a world with no detectable atmosphere at all, a frozen globe sealed under a layer of nitrogen ice with nothing above it but vacuum and starlight. This prospect carries a strange emotional weight. People who grew up seeing the New Horizons photographs, who fell in love with the blue haze and the heart-shaped nitrogen plane, may live long enough to learn that the atmosphere responsible for those features has ceased to exist. The blue haze will be gone. The volatile cycle will have stopped. The methane leaking to Charon's poles will have been cut off. The world they knew, the Pluto captured in those iconic images, will be a historical artifact, a portrait of a temporary state that the planet has since abandoned. But the atmospheric collapse, if and when it occurs, is only one dimension of Pluto's physical hostility. To understand why improved observation makes the dwarf planet feel progressively more alien rather than more familiar, you need to consider Pluto in the context of its broader environment, the Kuiper Belt. Pluto is not alone at the edge of the solar system. It is the largest known member of a vast population of icy bodies orbiting beyond Neptune in a region called the Kuiper Belt. This belt extends from roughly 30 astronomical units just inside Neptune's orbit to approximately 50 astronomical units from the Sun, and it contains an estimated 100,000 or more objects larger than 100 kilometers in diameter, with billions of smaller bodies too faint to detect from Earth. For decades, the Kuiper Belt was treated as a cosmic junkyard, a repository of frozen leftovers from the formation of the solar system 4.5 billion years ago. The objects in it were assumed to be inert, geologically dead, chemically simple, frozen relics, with nothing interesting happening on their surfaces or in their interiors. Pluto was considered the largest of these relics, and its demotion from planetary status in 2006 was partly motivated by the recognition that it was simply the biggest member of a large population of similar objects rather than a unique body deserving special classification. The James Webb Space Telescope has begun to demolish this assumption. Webb's near-spec instrument has been surveying trans-Neptunian objects as part of a large observational program called DISCO, short for Discovering the Surface Composition of Trans-Neptunian Objects. The program observed dozens of Kuiper Belt objects and centaurs, smaller icy bodies that orbit between Jupiter and Neptune, using near-infrared spectroscopy to determine their surface compositions. The results, published in 2025, revealed a far more complex and chemically diverse population than anyone had expected. The survey identified 3 distinct compositional classes among trans-Neptunian objects, each with different mixtures of ices and organic compounds on their surfaces. Some objects showed surfaces dominated by complex hydrocarbons and methanol, others were rich in carbon dioxide and lighter organics. Still others displayed water ice mixed with ammonia-bearing species. The chemical diversity was striking because it suggested that these objects are not simple, uniform balls of ice, but worlds with varied surface histories shaped by radiation processing, volatile loss, and possibly internal activity. This chemical complexity extends the lesson of Pluto outward across the entire outer solar system. Pluto is not an anomaly. It is the most visible example of a phenomenon that appears to be widespread among icy bodies beyond Neptune. These worlds have surfaces that are chemically active, responding to the thin drizzle of ultraviolet radiation and cosmic rays that reaches them even at enormous distances from the Sun. Their ices are being processed, broken down, recombined into new molecules. Organic compounds are being generated on surfaces where temperatures hover just a few tens of degrees above absolute zero. Consider what this means in physical terms. At Pluto's distance, the Sun delivers negligible warmth. At 50 astronomical units, the energy input drops to roughly 1/2500th of what Earth receives. Yet even at these extreme distances, ultraviolet photons and high-energy cosmic rays continue to arrive, slowly, relentlessly, and they continue to drive chemistry on the surfaces of every exposed ice body they strike. Methane molecules are shattered, nitrogen bonds are broken, carbon-hydrogen chains are built up into progressively heavier compounds. Tholins accumulate, the surfaces darken, redden, acquire complex organic coatings that transform their appearance and their thermal behavior over millions of years. This is radiation chemistry in conditions of almost total darkness, not the productive chemistry of a warm, wet, sunlit world, not the kind of chemistry that leads to life as we understand it. This is the slow, cold, destructive chemistry of a frontier where energy is scarce and molecular transformation happens one photon at a time over geological ages. The products are not biological. They are the organic equivalent of rust, complex but purposeless compounds accumulating on surfaces that no living thing will ever touch. Eris, the most massive known dwarf planet, orbits in the scattered disk at distances ranging from 38 to nearly 98 astronomical units. Its surface covered in methane and nitrogen ices, similar to Pluto's but brighter, possibly from fresh frost condensing out of a temporary atmosphere. Marke shows a surface dominated by methane ice, with a reddish tinge from tholin production. Haumea, one of the most unusual of the recognized dwarf planets, has an elongated shape from a past collision and a surface of crystalline water ice hinting at past internal heating. Each of these worlds presents its own puzzle, its own variation on the theme of frozen volatiles and radiation-driven chemistry. And Webb is systematically cataloguing their surface compositions, building the first comprehensive chemical inventory of the outer solar system. The picture that is emerging is not one of dead, uniform ice balls scattered through empty space. It is a picture of a reactive and restless region where surfaces evolve, atmospheres flicker in and out of existence with orbital cycles, and organic compounds accumulate in quantities that were never anticipated before direct spectroscopic observation became possible. Sedna, a distant object with an orbit that takes it from roughly 76 astronomical units at its closest to over 900 astronomical units at its farthest, represents perhaps the most extreme version of this phenomenon. Its surface shows signs of complex organic chemistry despite spending most of its orbit in a region so distant from the Sun that solar energy is essentially negligible. Whatever chemical processing occurred on Sedna's surface happened either during its infrequent close approaches or through cosmic ray bombardment over billions of years. Either way, the result is a surface that is not pristine ice, but a chemically altered landscape bearing the marks of long-duration radiation exposure. This broader context matters for understanding why Pluto feels more hostile the more closely we examine it. Pluto is not an isolated curiosity. It is the flagship of a population of worlds that exist in conditions fundamentally different from anything in the inner solar system. These are worlds where sunlight barely reaches, where temperatures are measured in tens of Kelvin, where the distinction between atmosphere and surface is blurred because the surface itself is made of substances that could become atmosphere if conditions changed by a few degrees. They are worlds where chemistry still happens, not because there is energy to spare, but because even a trickle of ultraviolet radiation, sustained over billions of years, is enough to transform surfaces into complex organic landscapes. And Pluto, sitting at the near edge of this population, experiencing the most sunlight and the most dynamic volatile cycle of any Kuiper belt object, represents the most active and extreme version of this phenomenon. Its haze-driven climate, its volatile ice transport, its atmospheric leakage to Charon, its potential atmospheric collapse, all of these are processes that may occur in attenuated forms on other trans-Neptunian objects. Pluto is the case study. It is the world where these processes are most visible, most measurable, and most directly revealed by Webb's instruments. But visibility does not equal comfort. The more clearly Webb reveals Pluto's physical environment, the less the dwarf planet resembles the cozy mental image that most people carry. Each new data point pushes Pluto further from familiarity and deeper into a category of physical experience that humans are not equipped to intuitively grasp. We understand cold, but not 40 Kelvin. We understand thin air, but not 100,000th of an atmosphere. We understand dim light, but not a sun that provides less heat than a candle flame at the distance of a football field. We understand seasonal change, but not seasons that last longer than the Roman Empire. The physical reality of Pluto is not simply that it is cold and far away. That much has been known for decades, and it is easy enough to acknowledge in the abstract. The physical reality, as Webb has now revealed it in thermal and compositional detail, is that Pluto is a world where the fundamental environmental conditions are so extreme that the processes governing its surface and atmosphere operate in regimes that have no counterpart in human experience. The climate is driven by organic haze rather than by any mechanism found on inner planets. The surface is made of frozen gases that sublimate and refreeze in patterns controlled by an orbit lasting 2.5 centuries. The atmosphere may be in the process of collapsing entirely, freezing out of existence over the span of a human lifetime. Molecules escape from one world and chemically contaminate another across thousands of kilometers of vacuum. None of these processes is scary in the horror movie sense. There is no monster on Pluto. There is no ancient alien artifact. There is no single terrifying discovery that can be distilled into a headline and forgotten. What there is, instead, is something more difficult to process. A steady accumulation of physical facts that, taken together, reveal a world so strange and so extreme that the comfortable, sentimental image of Pluto as a harmless frozen underdog becomes impossible to maintain. The outer solar system is not empty. It is not dead. It is not a vacant lot at the edge of a well-lit neighborhood. It is a vast, dark, chemically active frontier where icy worlds undergo transformations driven by processes so slow and so far removed from human timescales that they barely register as change. But they are real. They are measurable. And thanks to Webb, they are now visible for the first time in the mid-infrared wavelengths, where the truth of Pluto's thermal environment reveals itself most clearly. What remains to be confronted is what all of this means for the way we think about Pluto, and by extension, about the solar system itself. Because the deepest implication of Webb's observations is not any single finding about haze or volatiles or atmospheric collapse. The deepest implication is that Pluto becomes more unsettling the more clearly we see it. Better observation does not domesticate this world. It does not bring it closer to the familiar. It drives it further away, into a category of physical reality that is colder, darker, and stranger than the public image of Pluto ever suggested. And that realization, once it settles in, changes not just how you think about one small dwarf planet, but how you think about every frozen body drifting through the outer darkness beyond Neptune, in a region of the solar system that we are only now beginning to see for what it truly is. There is a particular kind of discomfort that comes not from learning something frightening, but from realizing that something you thought you understood was never what you believed it to be. It is the discomfort of failed familiarity. You recognize the name, you know the shape, you remember the story. But the more closely you look, the less the thing in front of you resembles the version in your memory, until you are forced to admit that the comfortable image you carried was never accurate. It was a sketch, a caricature, a simplified version built from distance, sentiment, and incomplete information. And now that better observation has arrived, the sketch dissolves, and what replaces it is something colder, stranger, and harder to accept. That is what the James Webb Space Telescope has done to Pluto. The process did not happen all at once. It happened in stages, each one peeling away another layer of the familiar image and replacing it with physical reality that pushed Pluto further from the cozy mental picture most people carry. And the stages did not begin with Webb. They began nearly a century ago, and each improvement in observational capability made Pluto less comfortable, not more. When Clyde Tombaugh discovered Pluto in 1930, it was a point of light on a photographic plate, nothing more. It could have been anything. A rocky world like Mars, a gas giant like Neptune, a body of any composition, any temperature, any character. The point of light carried no information about the world's true nature. It was a name on a map, and the map was almost entirely blank. People filled in the blanks with imagination. Pluto was cold, certainly, because it was far away. It was small, probably, because it was faint. Beyond that, everything was projection. For decades, Pluto existed in the public imagination as a vague, harmless, distant world, the 9th planet, the little one at the end of the list. A cosmic footnote. The Hubble Space Telescope provided the next stage. In the 1990s and 2000s, Hubble resolved Pluto as a tiny disk with blotchy surface markings, hints of complexity, but nothing sharp enough to interpret in detail. Pluto remained vague, still safe, still distant enough to be whatever people wanted it to be. Then New Horizons arrived in 2015, and the image changed dramatically. Suddenly, Pluto had a face. It had mountains and plains, and a heart-shaped feature that the entire world fell in love with. It had a blue haze that made it look ethereal and beautiful. The photographs were so stunning, so detailed, so visually rich that they created a new version of Pluto in the public consciousness. Not the vague dot of earlier decades, but a specific, recognizable world with personality and charm. People printed the heart on t-shirts. They used the images as phone wallpapers. Pluto became, paradoxically, more beloved after it was demoted from planetary status than it had ever been before. The photographs humanized it. But the photographs also began the process of disenchantment, because embedded within those beautiful images were details that, examined closely, told a story far less charming than the surface impression suggested. The heart-shaped plane was not a symbolic gesture from a friendly world. It was a basin filled with convecting nitrogen ice, churning in slow-motion cells driven by internal heat flow, refreshing its surface over hundreds of thousands of years. The mountains were not picturesque alpine peaks. They were blocks of water ice so cold they behaved like stone, jutting above plains of frozen nitrogen in a landscape where no liquid of any kind had existed on the surface for billions of years. The dark equatorial bands were coated in tholins, organic sludge created by radiation-driven destruction of atmospheric methane, a process with no parallel in any environment comfortable for life. The blue haze was not a sky. Not in any sense that a human being would recognize as sky. It was a suspended column of organic particles in an atmosphere so thin that standing beneath it would be indistinguishable from standing in vacuum. You would not feel air. You would not hear sound. You would not see blue above you. The haze is visible only when backlit by the sun during specific viewing geometries, a photographic artifact that creates the illusion of a familiar sky on a world that has nothing of the kind. Every detail, examined honestly, moved Pluto further from the familiar. But because the photographs were so visually compelling, most people stopped at the surface impression. They saw the heart. They saw the blue. They formed an emotional attachment to a version of Pluto that the data did not support. Webb completed what New Horizons began. By observing Pluto not in visible light, where surfaces look like landscapes, but in mid-infrared wavelengths, where thermal emission reveals the physical processes actually governing the world, Webb stripped away the last layer of visual comfort. There is no heart in the infrared. There is no blue haze frozen in an iconic photograph. There is a thermal signature showing surface temperature variations, driven by volatile ice migration. There is an atmospheric emission spectrum confirming that organic particles are radiatively cooling the atmosphere, in a process found nowhere else in the solar system. There is a chemical conveyor belt leaking processed atmospheric waste from one world onto the poles of another. There are declining pressure measurements suggesting that the atmosphere captured in those famous photographs may be in the early stages of freezing and collapsing onto the ground. This is what horrifying means in the context of this story. Not a monster, not a jump scare, not a fabricated shock twist designed to generate clicks. The horror is the progressive dissolution of a familiar image under the pressure of better observation. It is the realization that every improvement in how we see Pluto makes the dwarf planet harder to emotionally accept, not easier. The closer we look, the less Pluto resembles the version of itself that people carry in their imaginations, and the more it becomes something cold, strange, and genuinely difficult to process. This is an unusual kind of scientific discomfort. Normally, better observation makes things clearer, more comprehensible, more manageable. You study a disease and learn to treat it. You map a genome and understand how an organism functions. You photograph a distant galaxy and fit it into a taxonomy of known structures. Knowledge domesticates. Understanding reduces fear. The unknown becomes known, and the known becomes safe. Pluto reverses this process. Every new observation makes it less safe, less domestic, less recognizable. The discovery of its geological complexity did not make it feel like a familiar rocky world. It revealed processes operating under conditions that no rocky world experiences. The detection of its haze did not make it feel like it had a sky. It revealed an atmospheric cooling mechanism that operates by rules alien to every other atmosphere we have studied. The confirmation of volatile transport did not make it feel like it had weather. It revealed a surface that literally evaporates and reforms on timescales tied to an orbit lasting 2.5 centuries. Each finding is individually fascinating. Taken together, they compose a portrait of a world that resists every attempt to make it feel normal. And this is where the deeper discomfort settles in. Because Pluto is not some exotic, recently discovered object at the fringes of detection, it is one of the most culturally familiar objects in astronomy. Everyone knows Pluto. Everyone has an opinion about whether it should be a planet. Everyone remembers learning its name as a child, reciting the list of planets, placing it at the end as the smallest and most distant member of the solar system family. Pluto occupies a specific emotional location in the mental maps of billions of people. It is the underdog, the misfit, the lovable outcast. Webb reveals that the outcast is not lovable. It is alien. Its hostility runs so deep that even scientifically literate people rarely grasp the full scope of it. And the gap between the cultural image and the physical reality is so wide that bridging it requires abandoning emotional associations that have been building for nearly 100 years. This gap matters beyond Pluto. It says something important about how humans construct mental models of the cosmos and how resistant those models are to revision. Most people carry a version of the solar system assembled in childhood and rarely updated. A neat arrangement of named objects orbiting in tidy concentric paths. Each planet has a character. Mars is red, Jupiter is stormy, Saturn has rings. Beyond Neptune there is Pluto, small and cold and charming, and beyond that, nothing. Empty space. The end. This mental model is not just oversimplified, it is structurally wrong. It presents the solar system as a well-lit, well-ordered neighborhood where everything has been explored and categorized. The reality is radically different. The region of the solar system inside Neptune's orbit, the part that contains all 8 planets, all the named worlds, all the missions, all the photographs, represents a tiny fraction of the Sun's gravitational domain. The Kuiper belt alone extends from 30 to roughly 50 astronomical units, a volume of space vastly larger than the planetary region. The scattered disk extends much farther. The hypothetical Oort cloud, if it exists as theorized, may extend to 100,000 astronomical units, nearly halfway to the nearest star. In other words, everything most people think of as the solar system, all the planets, all the moons, all the missions, all the history, is confined to the well-lit entryway of a structure that extends into darkness for distances that dwarf the familiar neighborhood by factors of thousands. The solar system is a house where humanity has explored only the rooms near the front door. Beyond those rooms, corridors stretch into unlit wings that we have barely glimpsed, populated by icy bodies in quantities we can only estimate, undergoing chemical and physical processes we are only now beginning to detect. Pluto sits at the threshold between the known and the unknown. It is the last named world most people recognize before the darkness of the outer solar system begins. And Webb's observations reveal that even this threshold world, this most familiar representative of the outer darkness, operates under physical conditions so extreme that they defy easy comprehension. If Pluto is this strange, this hostile, this climatologically alien, what are the thousands of unnamed Kuiper belt objects like? What conditions prevail on worlds orbiting at 50, 60, 80 astronomical units, where sunlight is so faint that temperatures drop to 30 Kelvin and below? What chemistry occurs on the surfaces of objects in the scattered disk, bombarded by cosmic rays for billions of years in near-total darkness? The honest answer is that we do not fully know. Webb's DISCO survey has begun to characterize the surface compositions of dozens of trans-Neptunian objects, revealing chemical diversity that was never anticipated. But compositional classification is only the beginning. Understanding the physical processes on these worlds, their climate dynamics, their atmospheric behavior, their volatile cycles, will require sustained observation over decades. Pluto, the best-studied member of this population, has taken nearly a century of effort to reach the level of understanding that Webb's data now provides. And even that understanding is incomplete, contested, evolving. What Webb has accomplished is not a final answer about Pluto. It is a demonstration of what happens when a genuinely powerful instrument is pointed at a world that was previously known only through glimpses and snapshots. The result is not resolution, it is deeper complexity. More questions, not fewer. More strangeness, not less. The data does not simplify Pluto. It reveals layers of physical behavior that make the dwarf planet progressively harder to fit into any comfortable mental category. And this is perhaps the most important insight that emerges from the entire story. The impulse to categorize Pluto, to call it a planet or a dwarf planet, to assign it a rank and a place in a hierarchy, to decide whether it is important or unimportant, interesting or dull, is a fundamentally human impulse. We want to organize the cosmos into comprehensible units. We want to know where things fit. We want labels that tell us how to feel about what we are looking at. Pluto resists labeling. It is not a planet in the traditional sense. It is not an asteroid. It is not a comet. It is not a moon. It is a dwarf planet, a category invented specifically to accommodate objects that do not fit anywhere else. And even within that category, Pluto is anomalous, the largest member by volume, the only one with a confirmed atmosphere, the only one with a known haze-driven climate, the only one observed to chemically contaminate its own moon. Pluto is the solar system's most famous misfit, and Webb has revealed that its misfitting runs far deeper than taxonomy. The real shock is not that Pluto was reclassified. The real shock is that the more we learn about its physical reality, the more we realize that our categories were never adequate to describe what this world actually is. Pluto is not a small planet that failed to clear its orbit. It is a large, chemically active, climate-driven, icy world at the inner edge of a vast population of similar objects, operating under physical conditions that make it more alien than Mars, more dynamic than Mercury, and more unsettling than any gas giant moon despite being smaller than all of them. This realization challenges the implicit hierarchy that most people carry in their heads. In the standard mental model, size equals importance. Jupiter matters because it is large. Earth matters because we live on it. Pluto does not matter because it is small and far away. Webb's data explodes this assumption. Size tells you almost nothing about physical complexity or scientific importance. Pluto's haze-driven climate is unlike anything found on Jupiter. Its volatile ice cycle is more complex than anything occurring on Mars. Its atmospheric leakage to Charon has no analogue among the giant planet-moon systems. Smallness and distance did not make Pluto simple. They made it overlooked, and being overlooked allowed the sentimental image to persist unchallenged for decades. People could believe Pluto was a harmless snowball because nobody had the tools to show them otherwise. They could project warmth and affection onto a world they had never truly seen because the incomplete data left room for emotional interpretation. The heart-shaped feature was a symbol onto which people mapped their feelings about cosmic injustice and the unfair treatment of underdogs. The actual physical composition of that feature, nitrogen ice convecting in a basin that may have been formed by an ancient impact, was irrelevant to the emotional narrative. Webb makes the emotional narrative untenable, not by disproving it in some dramatic, confrontational way, but by filling in the physical details so thoroughly that the sentimental version can no longer coexist with the scientific one. You cannot simultaneously believe that Pluto is a cute, harmless outcast, and that it is a world where organic haze cools the atmosphere through a process that no other known world replicates, where the surface sublimates and migrates across the globe in response to centuries-long seasonal cycles, where atmospheric methane escapes across thousands of kilometers of vacuum and is chemically transformed into organic sludge on a neighboring moon, and where the atmosphere itself may be in the process of freezing solid. Both versions of Pluto cannot occupy the same mental space. One is a comfort, the other is a fact. Webb forces the choice, and the fact is harder to sit with. It is harder because it removes the emotional buffer that distance and ignorance once provided. When Pluto was a dot, it could be anything. When it was a photograph, it could be beautiful. Now that it is a thermal emission spectrum, a volatile transport model, a declining pressure measurement, and a confirmed haze climate interaction published in peer-reviewed journals, it is what it actually is. And what it actually is a world that operates in physical conditions so far outside human experience that calling it horrifying is not sensationalism, it is understatement. Consider, one more time, the full picture that Webb has assembled. A world smaller than Earth's moon, orbiting a sun that appears as a bright point in an otherwise black sky. Surface temperatures between -233 and -213 degrees Celsius. A surface made of frozen nitrogen, methane and carbon monoxide, the very gases that compose a breathable atmosphere on other worlds, locked here into ice harder than stone. An atmosphere so thin it qualifies as a vacuum by any engineering standard, yet thick enough to support a towering column of organic haze that controls the planet's climate through radiative cooling. A volatile cycle that causes the surface itself to evaporate and refreeze in shifting patterns over decades and centuries. Atmospheric molecules escaping from the planet's weak gravity, drifting across space, and settling onto the poles of a tidally locked moon where they are processed by ultraviolet radiation into complex organic tar. An atmosphere that may be in the early stages of collapsing entirely, freezing out of existence over the coming decades to centuries as the planet recedes from its distant sun on an orbit lasting 248 years. This is not a description of a harmless world. This is a description of one of the most physically extreme environments in the solar system, a place where every fundamental condition of existence, temperature, pressure, light, chemistry, atmospheric stability, occupies a regime so far beyond human experience that we lack the intuitive vocabulary to describe it, without reaching for analogies that inevitably break down. And the most unsettling thing about all of it is that Pluto is not unusual, it is typical. It is the largest and best-studied member of a population of thousands of similar objects occupying the outer solar system, a region that constitutes the vast majority of the Sun's gravitational domain and that humanity has barely begun to explore. If Pluto, the most famous and most accessible of these worlds, turns out to possess a climate system unlike anything found elsewhere, a volatile cycle of extraordinary complexity, and an atmospheric interaction with its moon that has no parallel, what might the thousands of unstudied Kuiper belt objects reveal when instruments powerful enough to characterize them finally exist? The answer, almost certainly, is more strangeness, more complexity, more physical processes operating in regimes that challenge current models, more evidence that the outer solar system is not the dead, frozen wasteland that the standard mental model imagines, but a chemically active frontier where icy surfaces evolve, atmospheres flicker in and out of existence with orbital cycles, and organic compounds accumulate in the near-total absence of warmth and light. Percival Lowell, the astronomer who initiated the search for Pluto in the early 20th century, called the hypothetical object Planet X. He imagined it as a large, distant world whose gravity perturbed the orbit of Neptune. He was wrong about almost everything. The perturbations were measurement errors. The planet he predicted did not exist. Pluto was found in the right region of sky partly by coincidence, and it turned out to be far smaller and far stranger than anything Lowell had imagined. But Lowell was right about one thing, even if he did not know it. There was something out there, beyond the familiar planets, beyond the well-lit rooms of the inner solar system, something that would challenge assumptions and resist easy comprehension, something that would become more disturbing the more closely it was examined. Webb has given us the clearest look yet at what that something actually is. And the truth it reveals is not that Pluto harbours some hidden terror or cosmic threat. The truth is quieter and, in its own way, more difficult to accept. Pluto is a real place, a physical environment with measurable temperatures, pressures, compositions and dynamics. A world governed by chemistry and physics operating at extremes that make it genuinely inhospitable in ways that the cultural image of Pluto has never acknowledged. The horror is not that James Webb found something monstrous. The horror is that the more seriously Pluto is observed, the less it resembles the harmless little outcast of popular imagination, and the more it becomes what it always was beneath the sentiment, a cold, chemically active, barely sunlit world whose atmospheric and surface behavior quietly destabilize the comfortable mental picture of a solar system that ends neatly at Neptune. Pluto does not become less frightening when seen more clearly. It becomes more so, not because it threatens us, not because it harbours danger in any conventional sense, but because it forces a confrontation with a version of physical reality that the human mind was never designed to find comfortable. A world where the air freezes and falls as snow, where the ground evaporates and reforms somewhere else, where the sky is made of organic poison drifting through a vacuum, where the sun is a cold point of light that cannot warm the landscape it illuminates, where even the atmosphere, the most basic prerequisite for a world that feels alive, may be a temporary visitor that comes and goes with seasons lasting longer than civilizations. This is what Webb saw when it scanned Pluto for the first time. Not a single revelation, not one dramatic secret, but a gathering portrait of a world that becomes harder to emotionally process with every new measurement, every confirmed prediction, every spectral line in the mid-infrared data that tells scientists one more thing about a place that refuses to be simple, refuses to be safe, and refuses to be the charming frozen underdog that everyone wanted it to be. Pluto is still out there, right now, tonight, drifting through the outer darkness on an orbit that will not bring it back to its closest approach to the Sun for another 2 centuries. Its haze is still glowing faintly in the infrared. Its volatile ices are still migrating across the surface. Its methane is still escaping to Charon. Its atmosphere may still be slowly declining, molecule by molecule, toward the point where it ceases to exist. And the James Webb Space Telescope, the most powerful observatory ever built, is still watching, still measuring, still revealing details about this world that no human eye will ever directly see, but that no honest accounting of the solar system can afford to ignore. The universe does not owe us a landscape we can emotionally process. It offers reality instead. And Pluto, seen clearly at last, is one of the coldest, strangest, and most quietly horrifying realities the solar system contains. Not because it is far away, not because it is small, but because it is real, and reality, at the edge of the sun's reach, looks nothing like the picture we drew when we could not yet see it clearly enough to know better.